Morning. Thanks for coming out. My name is Caleb Fox. As Dr. Kay said, I will be presenting on predicting MLB pitch sequencing with neural networks. So hitting a baseball is one of the most difficult tasks in all sports. Pitches can come in upwards of 100 miles an hour, and the batter has to be able to recognize the pitch, predict where it's going, and still have time to get an accurate swing off. Now, this becomes even more difficult when you consider the numerous types of pitches that pitchers throw. Now, how many baseball fans do we have in here? Have some? All right, now for those that are less familiar with it, I'm going to show a quick video. Now, this is called a pitch overlay. It's for Yu Darvish, so it shows all of his different pitches at the same time. So you can see how they move differently. So you can see as he releases the ball, they all come out from about the same spot and are on the same trajectory. However, as they move towards the plate, they all break into different directions and are at different speeds. Now, for a batter, you have to be able to hit any one of these pitches at any given time. That's nearly impossible, so how do they do it? Well, they simply guess. Batters are always predicting what pitch will come next, and they're trying to anticipate it, and will only swing if they guess correctly. Now, to help with this, scouting reports are constructed, very detailed reports of pitchers' tendencies, what they expect them to throw to the batter based off their tendencies. But the problem with these scouting reports is they're just based off of human observation. And humans are not very good at recognizing and predicting off of large data sets. So it leads us to the question of how can we apply machine learning techniques to improve these pitch predictions. So first, look at the research and some of the prior work that's already out there on this. Now, one problem with this is a very competitive question. In 2017, the Houston Astros stole signs with cameras, and so they always knew what pitch was going to come, and they won the World Series, which profited them millions and millions of dollars. So if a team can find a way to do this ethically and legally, they stand to profit a lot of money from this. So the teams that are doing research on this are not likely to make their research public. So we're limited to academic research and only found 4 studies on this exact topic. Now, the first approach is binary classification. So this simplifies the problem down to fastball versus off-speed pitches. There's actually many types of fastballs. You have 4-seam fastballs, 2-seam fastballs, sinkers, and cutters, all these things that move a little differently but are still fastballs. Then off-speed pitches would be like curveballs, changeups, and sliders. So this really reduces the problem down, makes it a lot simpler, easier to predict, but it's not as useful. It is a good starting point for our research. So the first study out of MIT in 2012 applied support vector machines and found a 70% accuracy, which improved significantly over the naive guess and showed some significant learning. Another study improved on this, looked more at input features and how they can improve performance. It got up to 75%. Now, this study only looked at 8 pitchers, so we can't really draw any big conclusions from their results. Now, the more interesting question is multi-class classification. So now, instead of simplifying it down to just fastball or not a fastball, we're looking at all the different types of pitches that a pitcher throws. Now, if we can get accurate predictions in multi-class prediction, this is very useful to batters. So instead of just saying he's going to throw one of his off-speed pitches, we can say we predict he will throw a curveball, and they can look for that pitch. So the first study was done in 2015 by Joel Bach. He applied multinomial logistic regression and support vector machines again, and he found an accuracy of 74%. Now, this is an extremely high accuracy, and I believe in looking over his data, it looked like there's some outliers that kind of skewed that, which we'll look at more later. But then the most extensive work was done by Glenn Seidel in his dissertation at North Carolina State in 2017. So he applied linear discriminant analysis, support vector machines, and classification trees. And these methods all produced about 65% accuracy. Now, his work extensively looked into different input features, and there's around 80 input features going in for any given pitcher, kind of varied some. These are some pretty significant results and show promise for machine learning in pitch prediction. Now, since that time, neural networks have exploded in popularity for machine learning. Neural networks have been around for a long time, but recent improvements in computational power may now make them very practical and very, very useful. So the purpose of this study, this project, we wanted to ask the question, do neural networks have the potential to increase accuracy of machine learning models for MLB pitch prediction? Now, originally we wanted to do a full-scale experiment and do prediction, try to get some high-quality results across all of the MLB, but we realized that was going to be way beyond the scope of this project. So instead, we wanted to first see if there's a potential for learning here that can potentially show some increased performance to previous methods. Now, a quick introduction to neural networks. It's a very hot topic. People have heard of them a lot, but not many people know how they actually work. Kind of seem like magic to some. They're not. They're actually quite simple. For anyone who has been frustrated in math class before and they just guess and check and find the right answer, and they're told it's not good enough, you'll love neural networks and machine learning because that's what we're doing. We're guessing and checking. So here's a basic diagram of a neural network. This is generic, so it just has different numbers of variables depending on how we want to structure it. But the basic structure of it is we first have an input layer, which is our x values, and each one of these nodes represents an input feature from our data. And then after we pass through the network, we will have this output layer, which are our y values or our predictions. So for a pitcher who throws 3 different types of pitches, they will have 3 output nodes, each one representing a pitch. So it could be a fastball, a curveball, and a changeup. So then our prediction will come out with a 1 in the value for the node we're predicting, the pitch, and zeros for all other nodes. Now how do we get there, right? We have to do something to get there, and that's the hidden layer. The hidden layer of nodes, you can have, this one we said 1, you can have multiple nodes, it gives you more deep learning. And they perform transformations on the data that produce our prediction. So this is called the feed-forward process. This is a very simple type of neural network, and we can calculate each node with this equation. So what this is simply doing is for a given node, so H1 here, we take the input value at each of the other nodes and multiply it by the weight connecting those 2 nodes. And then we sum all of them together. Now this produces our H value, but we still need to scale it down. So we call it an activation function. In this case, we apply it's the sigmoid function. It scales it between 0 and 1. So that's what we see here. We then pass it in there, and that scales our value down. We then repeat this process for the next layer, and we produce our output values. So once we have our predictions, we can calculate our cost, or think of this as an error. So we know from our data, with our training set, that we have the accurate classifications already. So we want to compare our results to what we know is already true. So our yi is our true value of output, and then our y hat is our predicted value. Now this formula down below, if any of you are familiar with linear regression, should be pretty familiar. It is the mean squared error. You can use different choices for the cost function. This is a pretty standard one. All it's doing is taking the difference of our prediction from the actual output and then squaring it for that specific node, and then doing it across every single node, summing them up, and then divided by how many nodes we have. And this gives us our cost or our error. Now when we create this model, we have to randomize all these weights, these values in here. It should be values between 0 and 1, should be normally distributed. But when we randomize it, we're very bad at guessing. It's going to be wrong. And so we need to find a way where we can find out what the correct weights are to produce a good model. That's where backpropagation comes in. Now this is where the learning occurs in the neural network. This is the crucial part. So the goal is to go back and adjust each of the weights to minimize that cost function which we just created. To do this, we have n is the iteration number and alpha is our learning rate, which is essentially how big of a step we want to take each time. And to calculate a new node for the next iteration, we just take the previous node's value, or previous weight's value, and subtract the alpha value times the partial derivative of the cost function with respect to that specific node. So this looks very simple right now. However, as we start to go back, we end up having chain rules to get back to that original, the first layer. And it gets very ugly and messy. Now, you would never want to do this by hand. This is where we let the computer take over. Now, doing it with an iterative process like this, it's very inefficient. Even if for a computer it takes a long time, fortunately, matrix representation significantly reduces the number of operations necessary, and it makes it very efficient and practical. So that's all I'm going to talk about for how the neural network works, just to give a brief introduction so you can kind of understand what we're trying to do here. So our method. Our data was collected from the Baseball Savant StatCast search. It's publicly available data. StatCast was implemented in 2017, and it stores a significant amount of data from every single pitch that happens in Major League Baseball. Again, as I said, if we wanted to do a full-scale implementation of this across the league, however, due to time constraints and resources, we limited it to 25 pitchers. So selected 15 starting pitchers and 10 relief pitchers. Really more interested in starting pitchers because they throw more pitches. It gives us more data to learn from. It's also more useful as they will pitch a larger portion of the game. So it's a good starting point. So we chose the starting pitchers who have thrown the most pitches in this time. And then relief pitchers selected the ones who had thrown the most or finished the most games this season and had not missed significant time for injury. This closing pitchers are traditionally used in more of a traditional relief role, where these days it's kind of been changed a lot, so I wanted to look more at closing pitchers. So now we had the data, we just shuffle it and reserve 20% of the data for testing and use 80% for training. So one very important part of creating these models is feature selection. So this is what data we're going to choose to train our model on and to make our predictions from. So as I said, we had to significantly reduce the input features compared to prior work. This is mostly just because of data handling issue. A lot of the information they used had to do with past tendencies of the batter, history of the pitcher facing that batter, and we would have to construct all those variables ourselves within the data. Certainly possible, but was going to be the most difficult part of the whole project, so we wanted to test the relevance on this first before doing that full scale. So instead, these are, you can see all the inputs selected there on the table on the right. And the categorical variables, we had to transform with one-hot encoding. So this transforms them into binary, so they can pass each one to a new node with just a 1 or 0 value. And then did normalization and scaling on the numeric values, which is just the score. So our method we used developed a backpropagation neural network, which is what I just talked about and demonstrated. Using the TensorFlow Keras package for Python, TensorFlow is most powerful and common machine learning package there is out there right now. And what this does is it didn't have to write the exact algorithm itself. Instead, just had to design the structure we wanted, test it out, and let TensorFlow do a lot of the work for us. So we explored both binary and multi-class classification approaches. As I said, we're really interested in a multi-class model that shows some success, but we still wanted to compare the success of a neural network in predicting in the binary problem as well. So the structure you can see there, it's just the different functions, optimization methods, and all that we selected. It's all the ones that I actually just talked about. And so I'm not going to really talk more about that, but you can change those to modify our network a little bit. So in the results, we trained the model with varying structures for each pitcher separately, because they all throw different types of pitches, so we had to consider each one differently. So we can graph our loss and our accuracy. Our loss would be our cost function, our error, across each epoch. An epoch is one pass through of all the data, and we'll do this over and over again. And so here's an example of these graphs for Justin Verlander, the binary approach. And you can see on the left-hand side, the loss is decreasing and then leveling off. And then similarly, the accuracy is increasing and it levels off here as well. Now this demonstrates that there's learning going on. If it was just completely random, then our models and methods are not working at all. All right, so now we can really dig down into the results from our method. So we established a naive guess, which was simply selecting the most common pitch that pitcher throws and predicting it every time. This provides a baseline that we can compare our model to and really see if we're having some learning going on. So in this chart, you can see the average accuracies for naive and the model output divided by methods and then by the different group of pitchers. So you can see here in the naive accuracy in this top row that relief pitchers are just more predictable, just even with the naive accuracy. They throw less pitches generally, and so they're a lot easier to predict. But then overall, our model had, in the binary case, a 67% average accuracy, and in the multi-class approach, a 49% average accuracy. Overall, on average, this was a 4% increase over the naive guess for the binary method and a 2% increase in the multi-class. And if we look more, we can see that starting pitchers, while they were less predictable, showed a greater improvement over the naive guess from a model than the relief pitchers did. So this gives us kind of a broad overview, but we still need to dig down a little deeper into the individual results. So the graphs or the charts on the right here is in the gray you can see the naive accuracy, and in the blue you can see the tested and validation accuracy for each pitcher's model. So for the starting pitchers with the binary approach, most predictable is Lance Lynn, least predictable is Aaron Nola, and then the greatest increase over the naive guess is Trevor Bauer. So you can see Lance Lynn throws almost exclusively fastballs. So he's very easy to predict when we have a binary approach. Now this changes significantly when we switch to the multi-class results. You notice it's much less predictable, but now our most predictable is Justin Verlander. And then our least predictable is Kyle Gibson, and our greatest increase over the naive guess was Rick Porcello. Rick Purcello, you can see him down here. Not very predictable, but a 9% increase is a pretty significant increase over the naive guess. Now, if we look at the relief pitchers, as we said earlier, they're much more predictable in general. And you can see Alex Colome and Kenley Jansen, they almost exclusively throw fastballs. It's very rare they throw anything else. And so the naive guess is already almost perfect prediction for Colome. And so then we don't have much room for improvement with our model. Now the least predictable is Rafael Montero, and the greatest increase over the naive guess was Brad Hand, showed more than a 10% increase, which is some significant learning there. And then the multi-class approach for relief pitchers, the most predictable is now Kenley Jansen, who we saw very predictable earlier as well. We also see Josh Hader, who throws mostly just his four-seam fastball, still very predictable. Least predictable is again Rafael Montero, and then the greatest increase over naive guess was Rafael Iglesias at about 5% increase. So there's a lot here, a lot to unpack. If you want to see more, I have more of the data in my paper. But what is this saying? Now, we can really see from here the pitchers that are already predictable, especially some of these relief pitchers, and even back with like Lance Lynn and Justin Verlander. The ones who are already predictable with their naive guess, we're not getting significant learning from our network. It's not doing much better than that. However, some of these pitchers that are less predictable, like Rick Purcello, Brad Hand at a big increase, are showing some significant improvement by applying our neural network. So then I wanted to look at separating these out is the starting pitchers and relief pitchers whose naive guess was above the average and below the average, and see if there's different results from our neural network, and if we need to apply it just to one. And you can see, except for the starting pitchers in the binary approach, most of the improvement over the naive guess occurs for the pitchers whose naive guess was below the average. Now, this is the one exception, as I said, is in the starting pitchers in the binary approach. This is because there were two outliers here, and they skewed the average and the mean up, and so there were only actually 3 pitchers above the mean there, and Trevor Bauer still had 8% improvement, even though he was above that average. So the real issue we have here is our sample size is still pretty small. So we can't draw like some big conclusions from this, but this is a big indicator that our neural network is producing some decent results and good learning from the unpredictable pitchers. So where do we go from here? As I said, this was not a full-scale implementation in pitch prediction. This is very much just a starting point. So we need to ask what else can we do, how can we improve this model, and then what can we build off in future exploration. So a few questions we need to ask. How can we improve the input features of our model? This is one that we significantly scaled down compared to prior work, and is I believe the reason that we don't see some similar performance overall to that prior work. Now, we still saw some pretty good prediction, especially for the less predictable pitchers, with a very small amount of input features. So if we can look at pitchers' tendencies historically before that given pitch, different history against that specific batter, I'd expect to really significantly improve our results. Another one is, can we increase the sample size? Starting pitchers threw an average of about 10,000 pitches in this time period, where relief pitchers only threw about 3,000. Now, 10,000 itself is already not very much for machine learning, but 3,000 is very little. So one question I wanted to ask is, can we train these models off similar pitchers to predict for one specific pitcher? So a pitcher that throws 3 specific pitches, can we train it off data for another pitcher that throws those pitches and then still get good prediction? If we can do that, this then allows us to predict pitch sequencing for rookie pitchers or pitchers with less experience. And this would be extremely useful. The scouting reports are not nearly as good on these types of pitchers. There's just not as much data out there. So if we can make this connection, this would be extremely helpful. Another thing we need to explore is, can we improve the design of our model, just different structures. We did try 2 layers as well in our neural network, and 2 of the hidden layers, and did not see any improvement. Most of the time it was actually much worse. So we simplified it back down to 1. Another thing is a committee approach could significantly help. Actually, Glenn Seidel in his dissertation proposed this as an idea. Committee approach is using multiple methods, so to be connecting a support vector machine and a neural network. And this could really get the best parts of both methods and has potential to see even better improvement. Another question is also asked by Joel Bach in his research. He was not able to answer this. Does less predictability produce more success for pitchers? You think that the less a batter could predict a pitch, the better the pitcher would be. However, we see some of these pitchers like Alex Colome and Kevin Jansen really don't care if you know what's coming. They're going to throw the same pitch no matter what. And this is a very important question, as at least a lot of other research, but we can't speak to it, as all the pitchers we looked at were successful pitchers in Major League Baseball. However, if we do find this to be true, why shouldn't we do completely random pitch calling? Baseball pitchers throughout history have had pretty standard methods that they choose their pitches by, until recently it has started to be challenged. So it was completely random pitch calling a better method. Or even more than that, more extensive research should go into, can we apply similar machine learning methods or other data science methods to find an even better way to call their own pitches. So as you can see here, there's a lot more work that needs to be done. Our model was not fully conclusive, but it does show potential for some pretty good results from a neural network to pitch prediction. So instead, we want to use this as a launching point into future research. Do you have any questions?
So you talked in the beginning about the obvious unethicalness of movie snap heroes and